All right, so what we're looking at is picking up kind of where we left off. So I have some brief notes here that kind of talk about what we're going to cover. I'll probably create a new diagram here in a moment. But let's go ahead and bring up virtual machines, see the example program where we left it off. And let's see. Looks like the example program I had a small error to it, or either that I was experimenting with something after class. Oh yeah, we don't want that. Don't think I did that during class.
I think you did, because you were like, let's try this right before class to see if it works, and then you're like, okay, that doesn't work.
Maybe I did it. I don't know if I did it for everybody. Maybe it was just for a few people, but yeah, that's not something that should have worked. What did we want to do? We want max word size of... Oh, I wanted to see if I could kind of make that depend on a variable for max word size, but I think I'm going to not do this constant that we had here right at the end. And we'll just put we'll do the malloc of 51 bytes there so that we can put a 50 in there. There might be a way to do what I was trying to do there, but I'm going to have to look up the exact syntax to see if it's possible. It's not terribly important. So let me go ahead and just so you can kind of keep up with what I'm doing, depending on how much of this you already had. Going to at least temporarily take some of this stuff out so I can get a nice screenshot. And we'll have it there for you to be able to keep up with. Oh, that's really okay. There it is. All right, so here's what we did before. Let me get that into the notes over here. So if I don't have it up on the projector and you're trying to keep up with what we had, that's now there in the notes. And so let's take a look at what we had and just kind of refresh our memory what was going on here. The idea was to write a program that reads in a list of words, and we don't know how big that list of words is going to be. It might be 5 words, it might be 10 million words, it might be 1 billion words. There's enough memory, we could probably squeeze 1 billion words in here somehow. So we don't know how many words, and this is where things like dynamic memory allocation and pointers start to become really important. If you're going to have dynamic memory allocation, you have to have pointers that point to the chunks of memory that get allocated so that you can access them and use them for things. And dynamic allocation allows you to select the size of memory you need for something like a list. If you only need a list of 5 words, you don't end up allocating enough memory for 10 million and vice versa. Yeah. Am I recording? I thought I clicked start. Okay, click to pause video. So now it is recording. Okay. Yeah, I think that's a few of the times when I didn't get a recording, it's because I clicked on that. It brings it up, but when you do that, it pauses the recording, and I think it's still going. I didn't notice that the clock on the thing wasn't ticking up anymore. But yeah, so right now it is recording, so we're good to go. And I don't like this font that I ended up with in here, so let me fix that. Yeah, where's the defaults font? Actually, maybe that's okay. No, that's terrible. I don't remember what the name of the default one is. It doesn't have a button here to just go back to the default font. Good grief. How did I do this? It's not horrible, but it's got so much space between everything. Ubuntu regular mono. That's either the default or close enough. All right, good. So what we had going on here was we were reading in a list of words, but we don't know how many words so ahead of time. So as a programmer, we can't just allocate an array of 10 or an array of whatever. And we also don't want to do the thing that we've done in the past, which is just decide a maximum size of the array and only use as much of it as we need. That's generally not a good, it's fine for simple little programs in a programming class, but in the real world, you don't want to have your programs using more memory than they actually need. And so if you don't need, if you want your program to be able to handle up to 1 million or 1 billion things, but it may only need to handle 5, you don't want to allocate all that memory for 1 million or 1 billion things if you're only going to be dealing with 5. So you want it to be able to adjust how much memory it uses. And that's where this memory allocation comes in. And for our purposes, we're creating a variable called word list that's just basically going to point to this structure of things out in memory that are going to represent our word list. And that's going to basically be the same sort of thing as the structure of that argv variable that we talked about. So let's refresh our memories there. I'm going to do that by just doing the diagram over again. But this time it'll be for word list. So our basic idea with word list is that it's a pointer. So word list is a pointer, and what I want you to start doing is, in terms of thinking about pointers now, is keep in mind that we don't usually care what the actual numeric address stored in a pointer is. Every pointer is just a number, all right? Basically an integer. It's probably an 8-byte integer instead of a 4-byte integer that you're used to working with, but it's basically just an integer, and that integer is just an address of some byte out there in memory. But we don't really care what that address is. What we care is what is being addressed, what is stored in that memory that's being addressed by the pointer. So when we diagram things, start thinking about things, what you want is to think of your pointer as an arrow that points to some other chunk of memory. And since we don't really care numerically, what physical bytes are out there, in a diagram, we can just diagram that chunk of memory kind of any way we want to, any way that makes sense to us. So word list is going to be a pointer to a whole array of other pointers, and each of those pointers is going to point to an individual word. That's the basic idea. So we can think of word list as pointing to some array here, and we don't necessarily know how big that array is going to be ahead of time. But we're going to have to allocate the memory for that array. So we're going to have to, at some point, it's going to have to be decided how many there are. But our program can do that dynamically. Can do that at runtime, decide how much it's going to do there. Then each of these is going to be a pointer out to another chunk of memory, which will be character arrays. Which is where we store the actual words in our list of words. Okay? So then we have another pointer and another character array. And another pointer and another character array. And so on and so forth. So that's the basic way to visualize what we're talking about as far as pointer to an array of pointers to arrays of characters. All right, that's the essence of what we want. Now I want to try to clarify what the data types of each of these things are. So first, let's say, let me just kind of highlight this thing in yellow. And we'll say that is, oops, it's not going to let me do it the way I want to. That's a char star star. All right, char star star. Star means, when you're declaring a data type, star means pointer to. So char star star means pointer, so that each star means pointer to whatever the type before it is, basically. So pointer to character. All right. So it's pointing to pointers to characters. So each of these boxes in this array, anyone, you can pick any of them, all right? Each of those is then pointer to character, so char star. And I think I'm going to duplicate that just to emphasize that each of these is individually a char star. So throw the purple highlighter on there. All right, so again, we're thinking of the pointers as arrows anchored at the place that they're stored. All right, but again, just kind of in the back of your mind, always remember it's really just a number that's being stored in each of those places that tells you where to find whatever it's pointing to. So now if we finally look at the individual boxes here, I guess I'll use green for this. So any individual box that we pick here is just a little one-byte character. All right, so this gives you the idea of the structure that we're building with this program. So now let's go back and look at our program and remember how we actually did that. So word list, our variable word list, that's a char star star, so we had to declare that variable. Everything else is created dynamically. There's no named variable that represents anything else that we have here in that diagram. So if we're looking at this diagram, we have a name for this box right here. Okay? That thing has a name. All these other boxes are chunks of memory that get created while the program is running and might even be destroyed, or, well, they're not really created or destroyed, but they're allocated by the operating system to the program and then given back to the operating system later. All of this stuff, there's no variable that names any of those things directly. All right? We can only access those things through the pointers to them. So in our program, we ask the user how many words are there going to be. That's so we know how much memory to allocate for our word list. And so we read that number that the user types in, and then we do this step right here. Word list equals malloc, and then what is in the parentheses for malloc? That's just a number. That's just an integer. We're calculating how much memory we need for this array. And we do that by taking how many things we want in the array. Is it going to be 10 words? Is it going to be 1,000 words? Whatever, right? And then we have to multiply that by the size of the thing that that array is made up of. And I actually made a small mistake here, because what are the individual elements of the array? What did I say? The type of each box in that array. Which
the individual or the actual?
Well, let's go back to the diagram so you know exactly what I'm asking. Word list is going to be a pointer to what? An array of these things. And what are these things? Specifically, pointer to char. But what did I use in my size of here? I said we're going to have this many of size of char star star. Technically not correct, but it doesn't matter because all pointers are 8 bytes. So that's going to, size of pointer to anything, at least on these machines, is going to be 8 bytes. So it didn't hurt the program to make that mistake, but it's kind of technically wrong. The individual boxes of that array are pointers to characters, so that's the type of those boxes. So I want to give size of the type of the boxes that I'm building my array out of, and size of will return the size of that thing. If I put int here, for example, well, if I just put car, size of car would be what? How big is a car? Car is 1 byte. Byte is 8 bits. A byte is 8 bits, but a car is 1 byte. So, but a pointer to something needs 8 bytes, so car star is going to need 8 bytes. If I put size of int here, then ints, at least on these machines and on most modern machines, int type in C will be 4 bytes. You could do long here. That would be 8 bytes. Double would be 8 bytes, and so forth. Or I could just do, instead of the whole size of thing, if I actually knew how many bytes it was, I could just say times 8. If I already knew that that's how big a pointer was, times 8 would work fine. But that requires a programmer to know it. And one of the things is when you take a C program and build that program for different machines, some machines might have 4 bytes per pointer, other machines might have 12 or 16 bytes for pointers or something like that. You don't really know. So to make your program, one of the points of having computer languages is that you don't have to change anything to run it on another computer. Or at least you want to have minimal changes to run it, to build and run it on another computer. That's where something like this size of comes in. First of all, you don't have to remember how many bytes are in a car star star or in a car star, as the case may be. The other thing is it makes it more portable. If you try to build this program for another computer, another type of computer, it's much more likely to still work on that computer. So just keep in mind that all we're doing for malloc is telling it how many bytes we want, and generally you can just break that down into how many items do you want in an array of things? Do you want just one of these items, or do you want a whole array of them? And if you want an array, how many do you want? Hence the variable name, how many. And you multiply that times the size of that thing. That's how many bytes you need, and you've got it. That's the number that you want to put into malloc. You could also, I mean, if you had a very specific number of bytes in mind, you could put however many bytes you want into a malloc command and get that many bytes. But that doesn't really help with the whole dynamic idea, because the whole idea is we want to ask the user how many items we need, and then we want to allocate enough bytes for that many items for our array. Okay, so that's word list. So we've taken the malloc command. The malloc command will ask the operating system, hey, I need this many bytes. Can you give it to me? The operating system basically says yes or no. If it says no, then malloc's going to return a null pointer. And to make a program bulletproof, we should check for the null pointer, which we're not doing here right now. But to make a program bulletproof, check for null pointer. So strictly speaking, we should do that if we wanted to make this a nice safe program that's not going to easily crash on us, because you never know if the operating system's going to basically say no when you're requesting for memory. And you generally don't want to just have your program crash if the operating system does say no. So all malloc does then is it returns the pointer to the memory that gets allocated. Now, if you didn't then save that pointer in a variable, like we're doing here, like if you just did this, well, you're allocating the memory, but you're not saving it in a variable that your program can access. So your program would never be able to do anything with this memory if we had it like this with just the bare malloc command. We need to take its return value and save that in a variable, so we use an assignment statement to store that pointer, store that address in word list. But we can actually think of the pointer as an arrow pointing to something, and we can kind of think of we're storing the anchor to that arrow into the variable word list. And again, that comes back to the diagram here. We store the anchor of the arrow in word list. Yeah?
Like if we don't use variable, like, does it get back to operating system?
It won't give it back to the operating system. That's a memory leak, basically. If you don't keep track of your pointers to allocated memory, and your program loses track of those pointers, the memory just stays allocated, because the operating system has no way to know that your program is done with it.
As long as the program is running, it's just...
Yeah, as long as your program is running, that memory is allocated. Let's see. So let's come back here. Okay, so that takes care of allocating the first part of this diagram, the array of pointers to arrays of characters. Now, initially, all of these pointers are garbage data, so you can kind of think of them as pointing off. They might be a bunch of zeros, but they're more likely to be garbage data, so you can just think of them as crazy pointers pointing who knows where. But whatever they're pointing at is not allocated memory that we can use or anything, right? It's whatever garbage data is in there for those numbers of those pointers. So we still have to allocate, we still have to request the memory that represents these arrays. So let's come back over to our program and see that. So how do we do that? Well, we have a loop, and in this loop we're kind of combining two things. We're allocating the memory for each new word that we read, and then we're reading the word and storing it in that memory. So here we're just setting a specific size for how much we want. We're saying basically each of our words we only want up to 50 letters in the word, So we reserve 51 bytes per word because there's always what at the end of a string? Null terminator, a 0 ASCII code, which is just a 0. And so if we want each word to be up to 50 letters or any characters, we make the size of the array to store it 1 larger than the maximum size that we actually want for the string. So this malloc then will ask the operating system for a chunk of 51 bytes. Say, is that free? And give me a pointer to the first byte. If the operator returns that, then we take that pointer and we store that where? We store that into one of the boxes of our word list. So
how is that a dynamic allocation? So we are already assuming our words from 51.
Well, dynamic just means it can change. Okay? Now, this 51 can't change because I just plugged it in there. But how many of them I get is dynamic. Okay? And the fact that it's not available until I allocate it is dynamic. Now, we could get even fancier and only allocate enough memory for each string. That would make this program actually quite a bit more complicated than the example I want to get at, because if you think about it, you don't know how many letters are getting, unless you ask the user, how long is your word going to be before each word? You don't know until you read the word how long it is. Maybe it's 5 letters, maybe it's 45 letters. You know, if it's deoxyribonucleic acid or something like that. Right? So you don't know how long the word is going to be. Now, in a program where you're dealing with words, words are usually pretty short. A maximum size of 50 is not that bad. I don't really care if I waste a few bytes on each word by having a fixed size for that array. As long as I don't have a million 50-byte chunks already pre-allocated. That would be 50 million bytes of allocated memory. That's getting a bit unwieldy if I only need to use 10 of those things or something. But you could do it. You could read the word. Now, you'd have to have a pre-allocated array. Maybe you allowed that your words to be up to 1,000 bytes long. You'd read the word, then you'd have to see how long the word was actually, the word actually was that you read in, get that length, then use that length in your malloc, okay, to allocate just enough memory for that one word, and then use that as what you point to for the word. You could do that. That's perfectly legitimate. It would add probably 20 lines of extra code to my program here, and that would be too much to throw at you as an example. I think wrapping our heads around this is bad enough without adding those layers of complexity. So we've allocated the memory, and then we just do a regular scanf for a string. We limit the size so we don't go outside the boundaries of our string. And we give it as the pointer to where to store the characters it reads for the string as word list box I. So again, looking at our diagram, each box that of the array that word list points to has the normal indexes 0, 1, 2, 3, and so forth. So whatever I is, we're picking out that box here. So if I happens to be 3, then we're picking out box number 3. So we just allocated this memory, and then we got the pointer to it, which means we can kind of think of sticking the anchor of the arrow that pointer represents as being in box 3. And so that points to another chunk of memory. And then that loop goes around. So this for loop goes around. I goes then from 3 to 4. We allocate another chunk of 51 bytes. So if we come back to the diagram, we would be getting another chunk allocated here. And then we return the pointer to that chunk, and we store that pointer into box 4 of word list. So that arrow gets anchored there and points to the new one. So that is the basic idea of how we're actually creating and building that list. So this is kind of a review of what we did last time, but I figure, it's been 10 days, 11 days? 11 days, probably worth reviewing. Now, once we have that list, let's think about how we can sort it. Well, you already have seen how to sort things with an array of numbers. So the idea here is that we have to have some way of comparing strings to decide which string comes first. And if we can do that, then it should work. The sorting should work very similar to the way we've sorted numbers. We can do the bubble sort or some other variation of sorting that we've seen. Actually, I'm not sure if it was the bubble sort. I think I showed you insertion sort, or maybe it was a selection sort. But they're all very similar in the way they work. Each method of sorting basically just means we have to swap things around. We scan through, we find things out of order, we swap them to be closer to being order, and we keep doing that and doing that and doing that until it's ultimately in order. I mean, that's one way or another, that's how a sorting program is going to be doing its job, right? So we can kind of have the basic structure of that already. I think I'll throw down one that does what's called a bubble sort. This might be a little bit different than the way we sorted before with the numbers. We could do either one, but I'm going to have a for I equals 0, I less than how many, because that's how many words there are to sort, I plus plus, and we'll open up a curly brace there. Then we'll have a for j equals zero, j less than how many, j plus plus, and this is very similar to what we've seen before. And let me just throw in a comment here. So we're going to make one pass through the list, is the basic idea here. So J is making one pass through the list, and the idea is we look at each element of the list and compare it to the next element, and if they're out of the order, we'll switch them. Okay? And then we go down one step, and if they're out of order, switch them. And go down one step, if they're out of order, switch them. We do that all the way to the bottom, and then we go back to the top, and we do that again. And back to the top, and we do that again. And if you think about it, if you keep doing that, the first time through the list, the thing that should be last will get pushed down, 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 down until it's at the bottom. And then if we do it again, the thing that should be second to last will end up getting pushed. So a few other things will get more in order than they were as well. But what we can guarantee each time through the list is that the next to last thing will get pushed all the way to the end, or to its position. So that's the idea here. So what I want to do is compare, and we'll just put it in comments for the moment. So we're going to compare the jth element, or the jth word, since these are words. So we'll compare the jth word to the j plus 1th word. Okay, so comparing the jth word to the next word, and if out of order, swap them. That's the essence of a bubble sort. Okay, the way I'm doing this one. I don't remember if I showed you a bubble sort last time we looked at sorting, but this is just a little bit of a different way of doing a basic sort algorithm. Now, there's one issue here. Even if we don't worry about how do we compare two strings or any of that stuff, and how do we swap pointers, forget that. Do you see, just with the basic structure here, this is coming back to sorting, which is a different topic than pointers, but I like to keep you on your toes. So I have one small mistake. Do you see what might go wrong here? And I'll give you a tip. If I want to compare the jth word to the j plus 1th word, do you see any time in the process of going through this loop where we could have a problem?
At the end, you're going out of bounds.
Right.
To increase it by one.
I'm letting j go all the way to the last index because it's j less than how many. And if I let it go to the last index, then j plus 1th, the j plus 1th one doesn't exist, right? That's going to probably cause some kind of problem. So now it's the kind of thing that if you don't think of it when you're writing your program and then you're trying to debug your program later, your program might do something strange. Like, why is it doing this? But this is the kind of thing you have to think through when you're writing your own programs. So let's just have j go say less than how many minus 1, and that should be okay. There are some tricks with the bubble sort that I could actually make it avoid some extra work, but I want to keep it simple right now. So if you spot those tricks, great, but we won't worry about them right now. So how do we compare the jth word to the j plus 1th word? That's going to involve, I gave the hints before, but if nobody really looked at this over break, you probably forget what's. But that's going to involve the strcomp function from string.h. So you might want to Google that and see if you don't already know how it works. Let's see, what are we doing for time? 2:15, right? Yeah, okay. So we got a lot of time. So we're going to use strcomp from string.h to deal with that. But that doesn't really have much to do with pointers right now. So I actually want to think about this, if they're out of order, swap them question. How do we actually do that? How would we actually do a swap? Well, we want to do something like, conceptually, we want to do something like this. We want to say, have a temporary variable and have that equal, well, I'm just going to say have that equal the jth element, and then make the jth element equal to the j plus 1th element, and then we want the jth, or the j plus 1th element make that equal to temp. And I suppose that's not real code, so let's make all that comments there. So that's the idea, and that's we did that with sorting integers. So we've seen swapping before, and so this will actually work just fine for pointers as well. Remember, the pointer is just really a number stuck in those boxes as well. So we can actually do this with the pointers, and when you visualize it, let's come over here and actually, I think I want to do a new page. And I'm going to do a quick diagram here. So if we have our array of pointers to the strings, to the words, and initially we can think of these as being nice and neatly organized, but here I'm actually going to fill in words. So like, I don't know, let's say here's the word this, and here's the word that, and then we have another word that is anything, like so. Now, assuming we can compare these two things, which one should come first alphabetically? That should come first. So if we're starting by looking at j equals 0, so if j is 0 here, then this is j plus 1 is that. So this is j equals 0, and j plus 1th element is that. We want to swap them. All right? Now there is a kind of a bad way to do this, which would be to have a temporary array here, and we have to copy all of this over here. Okay, then we can copy that up to there. So I don't know, I have to do some erasing. Wait, there's a button on here that lets me erase. See if we can get it to work. Oh wait, no. It's supposed to be able to turn it around like this. I remember now. Hey, it works. So that would get copied up here. And then we can take what's in the temporary variable and copy that whole word there. All right? And so this and that got swapped around. You could do that. But there's no reason to copy all of those individual characters from one string to the other and back to the other. All you have to do is leave those words right where they are. Get rid of all that. All we have to do is swap the pointers. So what I can do, well, what I think I want to do is just have this happen. Okay? Now the list is sorted. Now in our diagram it's starting to look tangled up because our arrows are crossing each other, but the computer doesn't care because those arrows are really just numbers to some place in memory, and it didn't really matter where they were in the first place. Okay? So if you're going to diagram your sorting and end up with whole things that were originally nice and neatly parallel arrows and all that, you may have one arrow going from the top all the way to the bottom, and then this arrow going there, and that arrow going there. But normally we don't sit down and diagram. I'm just doing the diagram so you understand what's going on. Okay? You don't have to manually change these diagrams all the time. But just to take the example one step further, we want to then, well, which comes first, that or anything? Anything comes first. So once again, we would want those two arrows to switch and, oops, not those two arrows. Which two arrows are we switching?
First and third.
The second and the third. I accidentally erased the first one. Because, actually, whoa, yeah. I made this a little, I confused myself a little bit. That's why these diagrams only go so far. So remember, our idea is we're looking at successive pairs. So if we back it up a little bit, let's just actually, here's the first three things in the list, right? And first we're looking at this pair, j equals 0 and j and 0 plus 1. J plus 1 is 1. Okay, so we're looking at that pair and deciding whether to swap. So we do that. Boom, boom. Okay, by switching those around. Now, what's the next thing that we're swapping? No. Well, we might, but that's not how I wrote the program. So I think the integer one, the sort I gave you for the integer would have compared 1 to 3. But the program I've written here is going to compare 2 and 3. So j is going to go to 2, and then we're going to compare, or I mean j is going to go to 1, and then we're going to compare j equal 1 to j plus 1 is 2, so we're going to compare the first to the second. And then we'll compare the second to the third, then we'll compare the third to the fourth, and so forth. Okay? Trust me, it works. Okay? Actually, I might take a sidetrack to make it more clear how that works, just like with numbers. But for now, just accept that I'm comparing these two. I'm comparing the second to the third one. So the second one is now pointing to what? This. And the third one is pointing to anything. So, yeah, that's fine. And just for grins, just to make this a slightly more complete example, let's throw zebra here as the fourth word. So right now we're comparing the second to the third, but the second one is now pointing to this. So we're comparing this to anything, and those are the two that need to swap. Anything clearly comes before that. So we're switching these two arrows. So this arrow is now there, and that arrow is now there. So before we go on, what is the first word in the list right now?
Anything. That.
Who says anything? Who says that? Okay, what is, you changed your vote after you saw the whole class. I'm sorry? That is the first word, yes, because what determines what is the first word is the array of pointers. So the first pointer here is pointing to that. Now, if I really wanted to like redraw everything, I could move everything out so our arrows aren't crossing each other. But right now, that is the first word. Eventually, anything should get ahead of that. But let's go ahead and continue the example. So now we want to compare the third and fourth items. So now we're comparing those. So what two words are we comparing? This and zebra, and which one comes first? This. So what do? Nothing. So then we go on and compare the next two words. So now we compare the fourth and fifth word, and yeah, might as well take it one step further. So now let's say, I don't know, we have lion here. Not really keeping a good theme with my words today, but whatever. So what comes first, lion or zebra?
Lion.
Lion. So what's going to happen?
Pointers switch.
We want the pointers to switch. Yeah. So now what is the third word in the list right now?
Yes.
What is the fourth word?
Lion.
What's the last word? Well, the fifth word. We don't know if it's the last. This might go on for more words, but
Zebra.
zebra. All right. So, and notice that at least out of these five, what one should be the last word in the list when it's finally sorted?
Zebra.
Zebra. And where is it right now?
Last.
It's last. So by making one pass through these five words, we've locked in the last one. Okay? Now you were asking, how will this process work? Let's do it again. So if we do it again, then the second to last word should get locked in. And then we do it again, and then the third to last word should get locked in. Okay? So I think that is a different way of sorting than the way I showed you before. I think I showed you compare the first to the next to the next to the next to the next, and just always swap to the first position. And then you move down, and then you lock in the second one, and then you move down and you lock into the third one. They're really kind of similar, but each method has its differences. All right, so that's the basic idea. Now there's one thing I left out of this diagram. Let's just do one more word here. So let's say we have fish, starting to get an animal thing going. And then this is what's pointing to that. So once again, what two words are we looking at? We're looking at the fifth and sixth. So we're looking at those two words, or those two pointers pointing to those two words. So comparing zebra and fish, right? So do we need to swap?
Yes.
Yes. Now I'm going to get a little bit more technical on you. So let's do the swap one step at a time. So we want to have this position point to fish, say. If I can erase it. So that's step one, maybe. Now, I would like to have the next one point to zebra. But if I actually wanted to get a pointer to zebra that I could copy there, where am I going to get that from? I've lost my pointer to zebra, right? If I just do it this way. So we still have the whole temporary variable idea, but now our temporary variable needs to be a pointer. So if we really want to do these swaps correctly, whoops. Actually, let me do this. Let me undo back to here. If we really want to do these swaps correctly in our diagram and fully understand what's going on, we need a temporary variable that is a pointer, just one plain pointer to character. And what we need to do is first we need to say, okay, make temporary point to zebra. And we can do that pretty easily. That you can assign pointers just like any other number. So I can say temp equal word list box J. Okay? Then, now that I've saved an anchor to an arrow that points to this thing, now I can safely change what I have over here. So now I can take this and I can say this box, word list box J, I can now say equals word list box J plus, actually let me zoom out just slightly. Box J plus 1. And that will take care of making this arrow point to the same place as that arrow. So now those two, word list J and word list J plus 1, are now pointing to the same thing. And now finally I want to say word list J plus 1 equals temp. And so now that will point to the same thing temp is pointing to. So I can erase that. Oops, erase both of them accidentally. That one still points there, but now that one points there. So when you still need a temporary variable, but the temporary variable itself is just a pointer. So coming back to our program then, we can see how that actually looks. So I'm going to say if, and for now I'm just going to say if we need to swap, and we'll come back and fill that in later. All right, and let's just go ahead and put in the swap. Well, we just had it over there in the diagram. I showed you the actual C code. So we're going to have temp equal word list. I think I use a capital L there. Yep. Word list box J, and then word list box J equal word list box J plus 1, and then we want word list, not world list, word list box J plus 1 equal temp. And that swaps the pointers around. So now we just have to figure out how this if we need to swap thing comes in, and that comes back up to the tip that we need to use this strcomp function from string.h. So just open up a browser window and Google for strcomp, Google man page strcomp or tutorials.strcomp. And since we have more than 15 minutes left, I'll let you see if you can figure out how you can use that function to actually, and you might do one or two instructions before the if and then put something here. You might figure out a way to put it all inside the parentheses here. I'll let you think about it, but Google the strcomp function, see if you can figure out how to use it to make this if do its job. So you need to figure out what to change here, where I said we need to swap, if we need to swap. You need to replace that with something, and you might need to put something before that to make it all work, depending on how you want to approach it. So I want you to get used to, pulling up documentation on functions on your own. So let's go ahead and I want you to give you at least till 2:05. So that's 7 minutes. See if you can figure out how to use strcomp.
String is less than or more than. What does that mean? What if the first string is less than second?
Basically, assume it means alphabetical. It's not quite alphabetical, but we'll get into details later. Okay, so it's going to compare the two strings and decide which one comes first. Just leave it at that for now. Okay, less than means it comes first. Greater than means it comes second. Equal means they're the same string.
while comparing the strings, we'd also take the garbage data, like if there are
If
five-
you gave it a string that was pointing to garbage data, it will try to compare them still.
So we're at least like so 5. There's 50
Mhm.
bytes, right?
Oh.
Allocated.
Oh, I think I see what you're saying. So if it's a shorter than 50, if the string is
Yeah.
short, like 5 letters or something,
Yeah.
so you have all the garbage data in those arrays. String always means ends with a 0 terminator. So it's only going to compare up to the 0 terminator. So if you have ABC and ABCD, and you compared those two, it would actually say ABC comes first. So if it's like, if you have 2 strings that are identical, but then one's longer, the shorter string comes first. But it doesn't like go past the null terminators on either string and look at the garbage data.
What are winners and like array of integers?
Mm-hmm.
What happens then
Well,
if it was an array?
okay, but you're talking about integers as text characters?
No, this integers.
Well, you can't give it integers. You have to give it strings. So string is an array of text characters, an array of car. So it's actually really only comparing those. I think after I've given you, after we get to hit 205, I'll kind of explain in more detail what.
No, I got it.
Strcomp does,
This
but
is a string function.
yeah, it's a string. It's a function for working on strings. Yeah, yeah. Okay, somebody got it or feel like they're close?
What are we supposed to do?
You got it? Think you got it? I think if you've got it, it should be finished and you can actually build and test it. I'm going to go ahead and show you what I would do. First, let's pull up documentation on that. So, two ways to search about if you already know the name of a function and you want to get information. Again, we've mentioned this before. Do a Google search on man page with that function name. You could put in tutorials point if you like the tutorials point website. You could just put C library function, name of the function, and get lots of different pages of various sorts that would give you tutorials on it, explanations, and so forth. But let's take a look at what we have here. So strcomp, it's a function that compares two strings, S1 and S2. It returns an integer less than, equal to, or greater than 0 if, strcomp. Oh, yeah, never mind. I threw myself off reading this. Okay, so it's gonna return either a negative, a 0, or a positive, depending on whether string S1 comes before string S2. Don't worry much about this const keyword in front of the char star. For our purposes, we only care about the char star aspect of this. Basically, the const there, actually I'll go ahead and explain. Basically, the const there is basically telling you that the function is not going to alter your string pointer. Okay? So it's kind of safe to use this on your strings without worrying about it changing your strings. That's kind of how you can sort of think about that. But you can pass it. You don't have to. Your string type that you pass it can just be plain char star. All right, so we're going to compare two strings. Basically, it's alphabetical. If you typed in all lowercase letters or all uppercase letters, it would make sense to you as an alphabetical comparison. I'll explain what it really does, hopefully before I end the class here. But so all we have to do is use this function, get its result, and look at its result to decide whether we need to swap. So over in our function here, what are the two things we want to compare? Well, the pointers, the char stars, the pointers to strings that we want to have it look at are word list j and word list j plus 1. So what I can actually do here is do strcomp. And I don't actually need to put anything before my if to make this work. And so I'm going to compare word list j and word list j plus 1. Okay, and then close the parentheses. So everything I have from here to here, that's strcomp. And now I basically want to say, is that less than 0? And I want to double check my comparison. So it returns an integer less than, equal to, or greater than 0 if S1 is less than a match or greater than S2. So less than, when we're comparing strings, when we're comparing words for alphabetical, less than means comes before. Just like with numbers, a lower number comes before a higher number. 2 comes before 3, 10 comes before 20, Fred comes before zebra. Okay, so Fred is less than zebra for this purpose. So what we know is then is that if S1 comes first, then it should be a negative result from strcomp. Okay, so I can ask if strcomp of those two things is less than 0, tells me if the first one comes before the second one, which means actually I don't need to swap. So I actually want to change that. I want to say if it comes back greater than 0. Either that or I have to switch the order I compare them in. So if the first one does not come before the second one, that's when we want to swap. Or actually when it comes after the second one. If they're equal, we don't really need to swap, so that's why I'm using greater than, not greater than or equal to 0. So that's pretty much it. That should take care of doing the comparison that we need, and then we have the swap happening there. So if I haven't made any other silly mistakes or left something out.
Initialize the temp.
Temp actually does not need to be initialized here because we're specifically going to put something in there when we need it. There's no point in here where I look at temp before I've put something in it. But, I mean, that's a really good question, though. His question was, do we need to initialize the variable temp? Now, do I need something up here?
You need to declare it.
Oh, declare it. Yes, we do need to declare temp. Right. Maybe that's what you meant. Okay, yeah, so we need temp, and I think I have a J now. Let's see, any other new variable? I think that's it. So we need temp. What type is temp?
Characters or char star.
Pointer to character, right. So just 1 star for temp. And then we also have a J that's just a simple integer for an index. So J, and that should take care of that. And I'm feeling pretty confident that I haven't made any other little silly mistakes here. So let's see what we've got. So GCC sort words example -o sort words example. And fatal error. What did I do? Oh, I forgot the .c for some reason. Oh, because I already had a previous built one. So when I hit tab to complete the file name, it only went up to before the dot because that already exists. Okay, there we go. So implicit declarations of stir comp. Did I not have my string.h at the top? Nope, I did not include string.h. So if we're using that stir comp function, we need pound include string.h. And again, if you look at when you're Googling things and looking at the documentation for functions, like here on the man page under synopsis, it shows you which include that you need if you want to use that function. So yeah, so let's go ahead and make sure I've saved that, and hopefully that's the last silly mistake. There we go. Now let's try /sort words example. How many words will I enter? Let's keep it short. Let's say 5 words, and let's go this, that, anything, zebra, and fish. And I didn't put any divider in there, but let's see what we've got. We got anything, fish, that, this, zebra. Is that alphabetical?
Yep.
All right, so far so good. So let's think about what strcomp actually does. That's what I want to leave you off with, talking about what strcomp actually does. I'm just going to do 2 words. And I'm going to do anything and zebra. What order are these going to come out?
Zebra.
Which one's going to come first?
Zebra.
Zebra came first. Because what we're really doing is sorting based on the ASCII codes. And so you think of the whole ASCII code as a big alphabet. So in English language, we just have 26 letters, and for alphabetical order, we don't care about uppercase and lowercase. But in the ASCII code, an uppercase letter is different from a lowercase letter, right? And the uppercase letters have a smaller ASCII code. So an uppercase Z comes before any lowercase letter, including a lowercase a. And the same thing applies to like numbers and so forth. So let's do one more quick example. Try this on your own. Just put random stuff, symbols like $, something. So spell something with a $, or
How many words?
we can do, oh, I forgot the number of words. Whoops. So number of words, let's go 4 words. I don't know, let's do leet speak here, and $, something, and 1, 2, 3, 4, and 99. I don't know, whatever. So let's see how they came out. So we see that $, comes before 1. Numbers, at least the number 1, comes before the letter L. And we already knew that the letter L was going to beat the letter N, so you could have figured that out already. So at any rate, if you just look at the ASCII code as one big giant alphabet, it's still doing quote-unquote alphabetical order, but with a different alphabet. Technical word for that is lexical sorting, if you're curious. So anyway, I'll throw a challenge out there to you. I know you're trying to get out of here. Well, it's still only 2:15. So challenge out there. See if you can make it do actual alphabetical order. You would actually have to do some conversion from uppercase to lowercase or something before you compare. So try that. Would be something you can try on your own before next class period.
Just like convert all to lowercase?
Yeah, either convert the whole string to lowercase or the whole string to uppercase and then do the comparison.